Okay, so today we're going to do precipitation reactions and percent yield. Okay, so what we're going to do is look at the question first, of course. If 25 mils of 0.15 molar lead nitrate is mixed with 20 mils of 0.2 molar potassium iodide, find the precipitate, the limiting reagent, the theoretical mass of precipitate formed, and the percent yield if we only get 0.805 grams of precipitate actually formed. Okay? So of course, the first thing we better do is first write this out as a balanced chemical equation. So here we go. Lead nitrate, so that's PbNO3 2 plus potassium iodide gives us potassium nitrate plus lead iodide. And if we're going to balance that chemical equation, of course, we would put a 2 here and a 2 here, and that would balance it just fine. So, what we're going to need is we're going to need that solubility chart that we've been using to see whether potassium nitrate and any positive ion of nitrate is soluble. So how about lead iodide? Lead iodide is not good. So lead iodide is going to be our solid. So this is our solid, or our precipitate. So that's PbI2. So there we go. There's precipitate. Now to find the limiting reagent, well, we don't know that, but that's what we'll do next. Okay? So now we can look at, okay, how many moles do we have of each one? So if I have 25 mils of 0.15 molar of this, how many moles of it do I have? So that's the thing, I have to find the number of moles I have of lead nitrate. So to do that, I can use my formula, which is M equals N over V. And I know that the molarity is 0.15. I know that the volume is 25 mils, so in liters, that's going to be 0.025. So now the number of moles is going to be whatever that times that is. So 0.15 times 0.025 gives us 0.00375. 0.00375 moles of lead nitrate. Now we do have to do the same thing for the potassium iodide. For potassium iodide, it's 20 mils of 0.2 molar. 20 mils of 0.2 molar. So it's the same thing. This is 0.2. This is 0.02. So when we multiply, we're actually going to get 0.0. Well, it'll be 0.2 of that. So it wouldn't be. So it'd be 3 decimal places. So 0.004 moles of potassium iodide. Now, here's the thing. Obviously, there's more of this than this, but we need to have, according to our molar ratios, we have 1 here, and we have 2 here. So in other words, we should have, whatever we have of this, we should have twice of this. And quite frankly, we don't. So because we don't have twice of the lead nitrate, we're going to run out of this first. Okay? We're going to run out of this a lot quicker. So your limiting reagent is your potassium iodide. Okay? Your potassium iodide. So the potassium iodide is going to drive the boat here. Potassium iodide is going to tell us how much lead nitrate we're going to use, how much potassium nitrate is produced and how much of the precipitate lead iodide is produced. So now we want to find the theoretical mass of precipitate formed. Now this takes us to our last unit, because I know that I'm going to be using this many moles of my limiting reagent, in other words, to figure out all the rest. So I know that according to my molar ratios here, I have 1 mole of this, 2 moles of this, 2 moles of this, and 1 mole of this. So I know that I'm going to have however many moles of my potassium iodide I have 0.004 moles of this. I know that the number of moles of this is going to be exactly, what's that? It's 2 to 1. So if I know this, how am I going to find out how many moles of this I'm going to have? Half of it, exactly. So in other words, I'm going to have 0.002 moles of lead iodide. And then if I need to find out the number of grams of lead iodide that I have, theoretically, then what do I have to do that? Exactly, multiply by the molar mass. What's the molar mass? Okay, well, periodic table is going to help me out there. Molar mass is going to be, what's lead? Lead is, better question be, where is lead? Lead's 207.2. Not sure what iodine is. It's 126.90 times 2. Did I say 126.9? I did. Times 2. So when the dust settles here, we're going to get 207.2 plus, that's 127, that's 254, 253.8, 253.8. So that's going to be 461 grams per mole, which is probably about the biggest molar mass we've seen in a while. So we get we have to take our 0.002 moles and multiply it by the molar mass. So the number of grams is going to be 0.002 times 461. Now that's going to be 0.922 grams. We don't have very much of it, so even though the molar mass is huge, theoretically we should only get 0.922 grams of it. Okay? Theoretically, that's how much we should get of it. Okay. Now, we're told that we have 0.805 is actually formed. So what's the percent yield? Well, part C is just going to be 0.805 divided by 0.922 times 100, which is going to be, actually I guess it should be part D, which is going to be 87.3%. So that's the percent yield. Okay. Next example. Next example. Okay? Alright, so now we'll write out the balanced chemical equation. So, sodium sulfate is Na2SO4 plus barium chloride BaCl2 will give you barium sulfate plus sodium chloride. Now, in these questions, there's never two precipitates. So, here's what I will tell you. I'll tell you that sodium chloride is definitely soluble. We'll verify, but I'm telling you that just by looking at this, I guarantee a barium sulfate is a precipitate. And, well, if I look at this, barium sulfate, barium, not soluble. Surprise. There we go. So this is your solid. Okay, there's your solid right there. Barium sulfate. So, we have to find out how many moles of sodium sulfate we have using the M equals N over V formula. So we have 150 mils of 0.5 molar. So 0.5 molar, 150 mils, N's going to be 0.5 times that, which would be 0.075 moles of sodium sulfate. Now what we're going to do is we're going to do the exact same thing for barium chloride. We've got 120 mils of 0.85, 125 of 0.85, 120 mils, so that's 0.12. N's going to be whatever 0.85 times that is. It would be, really? Would it be that? No, it can't be that good. I'm thinking. 0.102. Someone verify that for me? No calculators? Robert's on the job. 0.5 times 0.12, is that 0.102? Nice. Okay, so we gotta balance this equation first, I suppose. So I'm gonna balance it. I've got to put 2 here. I gotta put a 2. Would that only be the only place that would be a 2? Because I've got 2 sodiums, 2 chlorides, 2 sodiums, 2 chlorides. Nice. Okay, so it's a 1-to-1 molar ratio here. So with the 1-to-1 molar ratio, basically it's what do we have more of? We have more of this. So that means that's going to run out first. So it's going to be this that drives the boat. So we've got a 1-to-1 molar ratio. So if we have 0.075 moles of this, that also means that we should get 0.075 moles of this because the ratio is 1-to-1. So we know how many moles of barium sulfate we're going to get. So we just have to multiply that by the molar mass to figure out how many grams of precipitate we have. So for barium sulfate, barium weighs how much? Dropping everything today. Barium weighs 137.33. So molar mass is 137.33. Sulfate, I forget what that is. 32.07 plus 4 oxygens, which is 64. So that's going to be 169.4, 169. Is it 233.4? Is that what it is? I don't know. Yeah, it is. 233.4 grams per mole. So, what do I want to do? I want to take this and I want to multiply it by the number of moles to figure out the mass. So I'm going to take 233.4 grams per mole, multiply it by 0.075. That's going to give me 17.5 grams. Theoretically will form. Okay? That's how much will theoretically form. How much did form, according to the question? How much did form? Theoretically, how much did form, though? This is how much we should theoretically get. How much did we actually get? What's that? No? How much did we actually get? Yeah, 9.75. So we're going to take that and divide it by what we theoretically should get. So that's 9.75 divided by 17.5 times 100. And that will give us our percent yield. And we should get 55.7% as our percent yield. Okay, so there we go. There's 2 questions. Homework will be just like this. Yeah, there we go.